the cloud, and then I think everybody except Joan is muted. So I think we can mute Joan or and okay, yeah, she is. And I think just for safety, I'll make Joan co-host, because type of thing, because just in case I have an internet glitch. Because tomorrow they're coming to fix our internet. There is some problem with Spectrum. So hopefully it was glad it wasn't, and they did call us away. Okay, so
Spectrum's giving a new internet thing. It's really good. I just got it.
That's what they're exactly coming. So they were very nice about it. So, okay, so we're going to be talking about genes, and we're going to divide this section into two things, and is gene therapy and gene editing, So in two sections, type of thing, and some of the future trends beyond CRISPR, type of thing, because CRISPR is like, oh, that is so old, so to speak. It's, there are some new exciting things coming out as recently as the last couple of days, Now, I'm not exactly an English lit major, but those of you who are, want to take a guess where this is from? This could be, this is your chance to appear in Jeopardy. If you can remember this quote from your Shakespeare class or high school Shakespeare class. All right, I think Kevin Chittum and the other people, he's the literary man here, so he's not here. So this is from The Tempest, Act 5, Scene 1 and 2, line 203. And the reason for putting this, not to say that, not to look cultured, but this is for this, because this inspired this book, The Brave New World, that inspired Aldous Huxley's book in 1930. And, he really, this is before DNA analysis, just based on genes were barely being known. And he talked about the gene editing, and he was really like, ahead of his time type of thing. So, and, it's taken us, barely 60, 70 years, which is really not that long in terms of technology and the new things, but that has changed dramatically type of thing. And so much so that the word CRISPR has gotten into popular culture, I was listening to a talk, and that's when I heard about this movie called Rampage, so that talks about, some space capsule falls in and some animals get mutated with CRISPR, and they cause a rampage on good old Chicago type of thing. So that's like, I know it's an interesting movie, and I think somebody has pirated it and uploaded it on YouTube. So if you don't have Netflix or other stuff, you can look at it, type thing. So, but there is not much science in it, type of thing. So now basically, so there's a quote. We talked about Paul Berg, who was one of the earlier persons who did the genome work, before Jeanette, and did the E. coli and plasmid work in 1970s. And his quote from a few years ago in 1993 was, to be fluent in any language, one needs to be able to read it, write it, copy it, and finally edit it. And that's absolutely spot on, one can say, And now the two words are gene therapy means, it's they're introducing a gene, and that has been thought about from the early days after DNA sequencing, started, and as early as 70s, experiments were being done, and I'll have a lot more to say about it as we go along. While edit is actually correcting the code, that happened only after we were able to do the genome analysis, the human genome analysis, that. And various way you can edit these 3 billion letters. You can delete a letter, is the so-called knockout. And I may have, those of you who may remember, we talked about a knockout mouse. And here's this little funny picture, is the mouse that the leptin gene has been knocked out. Okay, so that's why the mouse is the other mouse, they're identical, except with the knockout of leptin gene, he just eats and eats and got fat. Okay, so that's where, that's a simple way. You're just removing one letter of the genetic code of the mouse. Similarly, there is inserting transgenic. Inserting means, so the GFP means green fluorescent protein. That is inserted. So those of you who watch Big Bang Theory, the lead character had a glowing fish on the side. Okay, so this is one of the hallmarks of green fluorescent protein that works as a marker for this thing. So that's one way you can insert. And this is replacing and knocking in. So this is the mouse that has the eyes that are becoming green type of thing. So so the various ways this explains what can be done with gene editing, basically. So it gives you a pictorial diagram type of thing. And I think some of the geneticists are very known to have good codes, type of thing. And there was in the early days of phage therapy, there was a South African physicist, geneticist named Sidney Brenner. And his quote is, "Progress in science depends upon new techniques, new discoveries, and new ideas." And again, until we discovered the technology of PCR, we would have never finished, we would have anywhere, it would have taken till 2150 to finish the genetic code. But the PCR technology just dramatically changed the things. So these are, so in a way, what he said does make sense that, without a microscope or electron microscope, we wouldn't be able to decipher the structure inside the chromosome, where centromere is, or what bands there are. So that's important, so the technology has work hand in hand type of thing. So there is, I said, I'll talk to you about this thing. The latest and greatest thing I look at MIT Technology Review, just for the fun of it, a couple of times, once a week. And just within the last few days, they have come up with a new tool. And I think now that, and we thought in medicine, we have acronyms and type of thing, but biologists are right behind us. The new tool, other than CRISPR, is now called PASTE, P-A-S-T-E. And that stands for Programmable Addition via Site-Specific Targeting Elements. So this is not just replacing one, but replacing a whole bunch of these things. So, and before some of you join in, so a word about gene therapy that I'll throw in case we don't cover everything. Just within the last 4 or 5 days, FDA approved a drug called Hemgenix, H-E-M-G-E-N-I-X, which is a one-time gene therapy product given as a single IV infusion for factor IX hemophilia that's expressed in the liver to produce factor IX protein. And so this is, remediates the bleeding episodes, the classical Queen Victoria inherited disease, And the cost of that is, hopefully you're sitting down, is $3.5 million. So that's one-shot therapy. So, and hemophilia is relatively quite common. So how that is going to pan out, as to time will tell, but that it has been approved officially. I know, but some of these drugs actually, they are not viable, some for the rare diseases. So even though, and before that, there was a drug that was approved, which was for another rare disease. And then the company finally just discontinued it because they didn't have enough market. So that's an interesting story. And the thing is, like, at least in US medicine, and to some extent all Western medicine, we are all fond of new technologies, like dialysis and transplants and other stuff. But the less glamorous things like controlling blood pressure or treating strep infections, to prevent kidney disease, are less glamorous. So the same way, before conception diagnosis is a lot cheaper type of thing. So instead of just screening, type of thing. So this is what we talked about, the Ashkenazi Jewish community, they're screening, and thank goodness they have been able to avoid Tay-Sachs disease. So it's a lot cheaper technology, but so I think this is, so enough philosophizing about this, but the cost and the a diagnosis before conception may be a lot easier and cheaper way to reduce some of this genetic burden that is there, that thing. And that is being done in rare diseases, and some of the gene editing, is like, basically it was a very crude, so you can just say it's like a Swiss knife, now with the CRISPR, things have been dramatically modified, that it has given us, even the genome editors, varieties of factors as to not just removing a bad letter, but inserting. So it's become a Swiss knife from a stone, basically. And these are some of the references for those of you who are more visual, learned by reading, And the code breaker was just almost like a homage to Jennifer Doudna, so who got was, it's a price, and so it's a nice Whodunit Unit by Walter Isaacson, and he's a very good writer, so you'll enjoy that. CRISPR People is by Henry Greeley, who's a genetics and bioethicist. He talks about this thing. Kevin Davis is an Englishman with a genetics PhD, and he's become a reporter for Nature magazine, and is based out of Washington, D.C. And this is a lot more scientific and very well-written book. As Gods is Matthew Cobbs. He's a Manchester-based geneticist, who has written about genomic code and varieties of books. Last but not the least, Beth Shapiro is an evolutionary molecular biologist. She has written things about reviving the old species that have gone extinct. So this will be enough reading for the Christmas holidays. And some of the earliest gene therapy attempts were done back in the 70s. People injected gene inside the leukocyte and gave it adenovector, but they didn't do anything. They didn't see any effect type of thing. But then the NIH scientists, were interested in pursuing this, matter. And they went to the appropriate ethic committees and tried to assess this treatment for hematological malignancies, and after varieties of reviews in 1982, presidential committee report was issued on splicing life. And so this was, the first ways to bring a consensus to the attempt at gene therapy. And after several reviews, some permission was given. Now, this was a good time because remember that this was just a few years after Nixon's war on cancer. And at the same time, I think, I was just starting practice, and this little report appeared, in the Morbidity and Mortality Weekly Report, pneumocystic pneumonia in Los Angeles. And that was the rise of the AIDS epidemic. So this was another good big reason, along with cancer, for looking up genetic treatment that was available, type of thing. So this was good incentive to start gene therapy at that time, Okay. And again, there was a man who is larger than life, and I think our friend, I don't know if John Hassel has joined in or not. Yes, he has. Yeah. So okay, so he can fill in. I think he has personal experience of the person named Dr. William French. He was an amazingly brilliant person who was a philologist, Harvard MD, PhD, worked on the genetic code, with Marshall Nirenberg. Okay, he also did some work on biophysics, and was a Rhodes Scholar. Had gone to Cambridge, and had his own lab at NIH, and he was, pushing for gene therapy because people, and in those days, the cancer treatment was horrendous, because I remember giving the chemotherapy drugs, and even with that, we made people a lot sick, and the outcomes were very poor. So there was a good reason to look for alternatives. And I think I may have mentioned earlier that this was the early days of immunotherapy also were done at Roosevelt Park Institute. So the cancer was the big thing, and people were looking for the holy grail for treating cancer in a different way. So this was finally, they got some permission to do retroviral gene therapy. And they obviously, they went for a single genetic abnormal disease. And a young girl, who was the so-called, quite a few of you remember the Bubble Boy movie, starring John Travolta, the severe combined immune deficiency syndrome. So this was a young girl. Her name was Ashanti De Silva, and she was one of the first patients who was treated with gene therapy for severe combined immune deficiency. And she had a deficiency on one particular enzymes, and she was treated with adenoviruses at NIH. And this was the protocol for the bacteriologist, for the people. No, it was a plasmid clone gene. This is the same way that insulin was synthesized when we talked about the early days of genetic testing. So, and it was T cells were isolated and were infused, under very close supervision with keeping your fingers crossed, a type of thing. So she was the first person to be treated for the SCID, with a clone gene. with a transfer with a vector and white blood cells. As you can see, the cartoon illustrates the procedure for those of you who are more interested in knowing about the procedure actual. So, and okay. And he had also, he had pushed very vigorously to get this. In fact, he had written a lead article in the New England Journal of Medicine in 1980, Gene Therapy in Human Beings, When is it ethical to begin? So that really, he carried a lot of weight, type of thing. And when the New England Journal raises this question, it just changed now as to who was more eager, whether the patients or the doctors. That question Matthew Cope raises, type of thing. So because obviously they were all willing to do the new experiments, and they had good intentions. Were they quite ready for it or not? Now, unfortunately, Dr. William French, or something bizarre happened that in 2004, then he moved on to California because his wife was a surgeon and he relocated to the warmer climates. And then he was accused of abusing one of his friends' young daughter. And obviously it was like in a sting operation with FBI. He was convicted beyond reasonable doubt and was sentenced for a fairly long sentence type of thing, and had to live on a home bracelet. And his wife still, until this day, he's like 85 and lives in California. But that's, the rise and fall of Dr. William French Anderson. And when I came across this, his Wikipedia page, I just fell out of his page, type things. And this is what an end to such. And he had written like several textbooks, published about 1,500 articles. So it's an interesting human interest story behind the rise and fall of Dr. William French Anderson. Okay, and John, if you have anything to add, please jump in. Okay. Yeah, I think. Okay, I think I figured.
He was really respected and admired, and I was quite shocked about this. His sex abuse problems, and I can see why it ruined him. I understand he spent time in jail still planning experiments with the expectation of getting out.
Oh yes, excellent, exactly. Yeah, so I think and he did some work on other biophysics also, something called microfluidics, and it reminded me the same thing. Microfluidics technology was the same thing that Elizabeth Holmes was interested in doing the blood testing. I said, wow, there must be something about criminal scientists, to be fascinated with microfluidics. It just kind of jogged my memory, So that was the woman who was jailed recently for the Tirano scandal. Okay, so that's an interesting side trait. Okay, so we better move along, type of thing. Science learns, it is not nice. Remember this commercial? Okay, and this is how the scientists learned. Okay, so this was, I think some of you may know about this, but it's a story worth telling. That at UPenn, this was this young man named Jesse Gelsinger. He had a metabolic disorder where he built up a lot of ammonia in his blood, and it was an X-linked enzyme deficiency, and he wasn't that sick, and he volunteered for this study type of thing, and he signed up for gene therapy, and he was able to control his treatment with diet and watching and some and ammonia lowering drugs, but still he volunteered to sign up for this treatment. About 2 or 3 days later, he had a multi-organ failure and died at age 18. And it turned out that there were some the people that the scientist, the principal scientist named Dr. Wilson, and University of Pennsylvania had cut some corners. They had their informed consent was not as well as that they had not reported that some of the monkeys that were done similar treatment had died actually, and they had given a lot larger dose than that had been used in testing other people. And also that his ammonia level when he was admitted was already a little on the high side. So, and it turns out that the science was that it was, everything, other than that, they followed this thing, but the virus, which was, not active, the capsid of the virus, which is the outer coating, that overwhelmed his liver and then he developed something called cytokine storm reaction, so enhanced immunological response, which is known in young people. That's what happened in 1918 flu epidemic also, a lot more young people died than the older people, because that body overwhelmingly reacted to the immune response was a lot stronger than what would be in people of our age. And so that caused the death. And Dr. Wilson shut down his lab, and he had to resign, so this setback gene therapy for vectors, several years, and to their courage or foolishness, the French continued with this, and they treated some people, some of the hematological patients with adenovirus, other things. And what happened was that 2 or 3 people, after successful treatment for SCID, that is the combined immune deficiency, they were successful. Their data was quite good, but they developed leukemia a few years later. So the French government also suspended the trial. So there was a huge learning curve that the geneticists and the physicians involved had to climb through that. And this was the name of the kind, and the name is not academic, but they treated about a dozen patients. Okay, now, but that doesn't mean this is the end of the therapy type of thing. So this is, a guideline for those of you who are history buffs type of thing. So, okay, and you can just say it brings us up to down to the T lymphocytes, the gene therapy type thing. So, and this is, anybody recognize who that is?
Richard Burton.
Yep, spot on, absolutely. I did not know that he had hemophilia. I was just looking at famous people with hemophilia type of thing. And now, why is this picture important? This is a kid. This was, remember, I showed you the slide in 1980. At the start of gene therapy, AIDS, HIV was there, and this is a young kid in in Indiana who had hemophilia and got HIV due to repeated blood transfusion. And the AIDS community and the gay community stood behind him. And this was Elton John in his younger days. He was a spokesman for Ryan White, and the family sued the school district because the school district would not allow him to attend school because of the earlier stigma of HIV. Type of thing. So this was the early days. So he was the poster child for the discrimination against HIV. And that fits in right way to the last case that we'll talk about, the gene therapy, about the Chinese scientists. So how, it makes sense. If it was this bad in the United States, it was probably a lot worse in China type of thing. So that gives the reason to the scientist, Dr. Hu, to do the gene editing experiment, but that is for more on that later on. Okay. So this was one of the types. And this is what I've talked about, that they said as recently as November 23, so you can't get more recent news than this, FDA approves a $3.5 million drug. So I think, it's like, they'll have to print a lot more dollar bills if they want to treat all hemophilias. And if it goes to similarly therapy is approved for sickle cell, it's going to be absolutely unreal that we'll have empty Fort Knox, basically. So that's the therapy. Now, again, this is the tragedy of the drug development that is done in university laboratories, as well as trying to venture with commercial outfit. Because one of this smaller pharmaceutical company, OSHER Pharmaceutical, that was doing the same therapy under more, with the better vectors type of thing. And this is a strike from UCLA, that they were willing to do therapy, but because they realized that this was not cost effective, so they decided to get out of the business. Okay, so the principal investigator and at UCLA, who was, I think his name is Dr. Cohn, he was doing it, and so they're kind of left, that their trial was, they were left holding the bag, so to speak. But the state of California has stepped in, and the latest is that they will be able to continue some of these trials. They'll be funded to at least some extent. So, and a lot of the drugs, some of the other companies also. Orchard is not the only company to give up the market, but they're in good company. A lot of other companies have also decided that it is not cost effective to develop these expensive gene therapy drugs. So that how it will pan out, that remains to be seen, type of thing. Okay, now, we've already talked about phages, which are tiny virus-like particles that attack bacteria. So we talked about in the earlier testing. So, and then we again talked about archaea when we talked about the three phyla of life, okay. Right. Remember that bacteria, eukaryotes, which includes all the mammals and fish and all the other animals, and archaea, which is the in-between kingdom that was discovered, by the scientists at the University of Illinois, and then the bacteria. So these are three, and obviously the other kingdom, which are, and this gives us to the idea as to what, and this is like the struggle for existence. It's like Jacques Cousteau used to say, struggle for existence continues. So archaea, archaea being invaded by phages, attack the viruses, so they have developed immune system, okay, and so that is where the CRISPR comes into the picture. The acronym, it's an evolutionary arms race between the various kingdoms. Now we haven't included fungi because that would be going too far into complex, but that's not our subject matter. So this is a palindrome basically, and I'm sure I don't have to tell any of you what is the palindrome, but my dad was a big admirer of Napoleon, and he always, I don't know whether he actually said this or not, but the quote that I heard as a kid was, "Able was I ere I saw Elba." So that is the classic palindrome that was attributed to Napoleon. I looked it up further. It was coined 20 years, the phrase was coined 20 years after his death. Okay. And so that's an explanation for palindrome. And not to disappoint Monty Python fans, which I happen to be one, in the famous parrot sketch, there's a word, go to my brother in Bolton. The palindrome of Bolton is not long, not Ipswich. Okay, so enough digressing to Monty Python. So I can say that I've stayed true to my thing. I have to mention Monty Python once at least. And so varieties of factors. Just to give you an example, for example, fungus. Well, a lot of the fungus, including penicillin, was derived from antibiotics and to kill bacteria. What has happened? Bacteria has fought back against the fungus by developing resistance. So to use the old axiom, enemy of my enemy is my friend. So we use phage now. And I gave you the example of phage therapy to treat antibiotic resistance. Okay. So phages are enemies of bacteria. So we are using phages, and we may go back to phage therapy type of thing, if we don't come up with new antibiotics, So, but that we'll talk more about it when we talk with Joe in our medicine class. So we'll have enough to pick on antibiotic resistance and the forthcoming problem. So this gives us the introduction on the CAFs. We'll spend some time on it, and I think I wasn't going to show you a video, but this just explains the immunity and the warfare that goes on between phages and archaea.
Bacteria use an adaptive immune system called CRISPR to acquire protection from viruses. When a virus injects its DNA into a bacterial cell during infection, a piece of the viral DNA is integrated into the bacterial genome, its genetic program, at a site called CRISPR that includes a series of repeated sequences that flank each inserted piece of viral DNA. This creates a permanent genetic record of past infections. Then, the sequences are copied into strands of RNA, DNA's chemical cousin, and the RNA is chopped into functional units, each containing one viral sequence plus the flanking repeat. The chopping process requires a separate RNA called tracer RNA that together bind to the Cas9 protein, a component of CRISPR immunity, to form a surveillance complex. Upon finding DNA with a matching sequence, the Cas9 RNA machine holds onto the matching DNA sequence, unwinds it, and cuts each strand of the DNA double helix. In bacteria, the broken viral DNA is chopped up and destroyed by other proteins, thereby halting the infection.
Okay, so this is, so that was the way the bacteria have evolved with their own defense mechanisms. And the start of that goes back to almost 1987 or so, that a Japanese scientist named Yoshizumi Ishino, he was doing the sequences, and he noticed that the sequences of various nucleotides were kept repeating. But then he just said, oh, that's unusual, but he didn't follow up on it further. So, and it took until then the scene moves later on, a few years later in 1996, to a microbiologist who was working with rare bacteria, which are the salt-loving bacteria, and on the Spanish coast. And he again noticed the same things, as to 14 sequences. By this time, biological gene analysis had advanced enough that he was able to compare some of these sequences from 1986 with, with other bacteria, and he saw that these were matching sequences. So that's when the first, he came up with the idea that this has to have something. These sequences would have to have a purpose. This wouldn't be there just for the fun of it, so to speak. And so that was the first hint of existence that came around. And then along with, then he was trying to come up with a name for it, type of thing. And he was in correspondence with another Dutch scientist, so because of these repeated sequences, they came up with the name. They were going to call it SPSR or something, or SPQR, that had to do with the Roman Senate, perhaps, and but then luckily they didn't choose this, type of thing. So and so finally they came up with the name CRISPR, which sounded very, easy to pronounce and did convey the meaning. So this were reported in a range of other bacteria as well, so a lot of the bacteria. So there was an important role of evolutionary conserved sequences. Okay. And similarly, some other people discovered this in France at the same time. So it was originally one of the European microbiologists who came up with, and this is, this was the start of CRISPR. And the scientist, he's considered, so Francisco Mojica, he's considered the El Padrino, or the godfather of CRISPR type of thing, But okay, and this is, this is how the genetic analysis is done. Like these are the sequences. The letters are, immaterial, but you can just see that the one that are in our outline, they are repeated in the genome analysis. How so they come around, type thing. And again, so this is CRISPR type of thing. But the George Church, who is like the who is who of molecular biology at Harvard, he says, well, this is a lot more impressive that there is just, this has another acronym that he has created. It gives you a lot of comprehensive data with recombination. Informatics, this is called analysis of all this data. It's called science of bioinformatics. And sequences, nowadays they can sequence things, at a lot blitzkrieg speed, basically, okay? And a pluripotency that has to do with stem cells. And again, the cost of sequences has dropped dramatically from $3 billion to less than $100, like we talked about. So this is another way that the data and next NGS means next generation sequences. Bioinformatics means doing massive comparative analysis. STEM means the sequence stem cells. So this is where all the two big advances of stem cells and CRISPR sequences, along with big data, is going to come together, hopefully, and it will. Okay, all right. So, and this again shows you the same slide which we saw in the video: the viral infection that gets integrated into the host genome, and the Cas protein. And obviously, when you say it, let's re-emphasize, when there is this big blob of protein, there has to be a gene somewhere. So there is a Cas gene, okay, and it forms this combined complex of two types of ribonuclease sequences called tracer and CRISPR RNA, and that combines along with the protein. And it next time it comes, say, hey, you're an invader. So that's when it eliminates, type of thing. So it and then. Okay, so let's move on. So this is, okay, the CRISPR in 1959 and CRISPR in 2011. So tandem repeats, that's how the name was coined by Janssen, who's a Dutch scientist, and Mojica. Okay, and this is for those of you who are interested in classics. This was the book by a classicist named Mary Beard on SPQR type of thing. So that's just so fortunately they didn't select that name. Okay, and again, from the movie, Blessed Are the Cheesemakers. Now here, this was not the cheesemakers, but the yogurt makers had an interesting role to play in the CRISPR. That yogurt was, for a small Danish company which made cultures for yogurt and cheese manufacturing. selling the cultures was a big business. So they discovered some of their cultures were spoiling. And so they came up upon, again, this bacteria sequence. And they, with the sequences, they analyzed, that this was the matching virus sequences. So they stumbled upon CRISPR independently on their own. The two scientists, named Barignou and Horvath, who were, European trained, but they were working with American companies. And one of them had moved from North Carolina to Madison. And so they're the ones who first, isolated this in the Cas9 gene. And they wrote the first paper in Science magazine. And they thought they were two humble working for a dairy company, and their paper was accepted. So this was the contribution that came from the yogurt industry, everything. And now the company is owned by, it's part of DuPont. So, and in the movie Life of Brian, there is a saying about blessed are the peacemakers, and then they mishear it as cheesemakers. So that's what I thought, that blessed are the yogurt makers who contributed to CRISPR. And as Thermophilus was the bacteria that they worked with, basically. Okay, and so much so that Dr. Barignou had his personalized license plate on his Honda in Wisconsin, was starting CRISPR, okay, which was, in many, so this was just the basic thing that we already talked about earlier. So for sake of time, we'll move right along. And this is, again, this just gives you the idea of the timeline as to how it took several years for the things to evolve, type of thing in CRISPR biology from 87 to 2012. So we're talking about good 20 years span as to systematically analysis was done, type of thing, until to the finally when the big paper appeared and then the whole world began to hearing about it. Again, although surprisingly, it took for a while for the newspaper to catch up with it. The reports in the New York Times and British newspaper took until about 2014-15 to appear on CRISPR as earth-breaking technology. And now, not to get outdone, even 60 Minutes just a couple of years ago had done a story on it. Okay, and similarly, their genome editing has also the varieties of things. We already talked about the knockout mouse that Oliver Smedes and Mario Capucci got the Nobel Prize for it. So it's already big given, but the recent advance was important enough to that we'll continue talking about it here. Yeah. And this is gene editing through the ages, type of thing. So this is, starting from early discovery of DNA to Watson and Crick, to gene editing with something called zinc finger that was used. That was the earlier technology that was used in 1996. Okay, this was done by an Indian scientist who was working in the US with getting zinc finger enzymes. And so this was done for gene editing, but it was a very complicated technology, and the data was not that adequately successful. So it was a very labor-intensive and challenging technology. And the zinc fingers were the varieties of factors that were identified in African clawed frogs, okay, in some laboratory on the East Coast, type thing. So, and as to this, always, I was thinking about it the other day as to how inorganic biology and organic biology are linked together, type of thing, as to how maybe either John or Peter can comment upon it as to how the metals got involved in, role of protein synthesis, type of thing. So this was, the same way we saw about hemoglobin, which is the iron molecule. So how the two main branches of chemistry, they overlap in this. So, and then a few years later, another technology that was developed, something called transcription activator like effectors, So this were varieties of transcription factors. So those were also used for, so these are, these are varieties of proteins. You can see how the zinc finger looks similar to this various enzymes, that cut the sequences in the right place. Okay, until again, but those were challenging, and with the discovery of CRISPR, these have fallen by the wayside. Although some labs still continue to use that, because they have more, they do have experience with. Okay, so this was, the varieties of kingdoms, like viruses, phages, and bacteria, they're overlapped, and we are using that evolutionary biology for our advantage for editing eukaryocytes, which are the cells with nuclei. But more on that later. So these are just the basics. So the CRISPR-Cas unwinds and directs. Okay, this was a cartoon from Jennifer Doudna's slides. Okay, relax, relax your backbone, let yourself unwind. And this is again, just shows in a cartoon figure as to how the DNA sequences are unbound by the Cas protein, which is in green. Okay, and the two types of RNA which are used, CRISPR RNA and tracer RNA. These are inside the green complex, and the sequence is matched, and their double-stranded breaks are created, and then the gene is inserted or deleted, in the correct spot by natural recombination procedure. Okay. And this is interesting, Lesto. And so there are varieties of steps that takes place. DNA is recognized, imaged, expressed, and changed. So, okay, and there are a lot more technical details on it, but I don't think you want to get too much into it as to how many base pairs there are or something. This again shows you the same thing as to how the protein here. Okay, this is the guide RNA, the double-stranded DNA, and how it is broken at this point. And okay, again, more of the same this thing, but I think I should have eliminated. And it just gives you some biography of the two principal researchers who were awarded for their discovery. So this was she was a young crystallographer and structural biologist, who started working on the West Coast at Pomona College, then got his PhD working with Jack Szostak, who is the RNA Nobel laureate, and then has her own lab at UC Berkeley. And she did some forays and going to work for Genentech for a little while, but did not enjoy working in the biotechnology world, and moved back to UC Berkeley. And then she was, just like it happens in science, she was contacted by various other people from different walks of life, some who are working in biology, and some who are working in, in other fields, and so that focused her on working on CRISPR, and that the rest is history, as they say, and type of thing. And before that, she had primarily worked with, because Emmanuel Carpentier is a microbiologist by training, and these two ladies got together at a conference in San Juan, Puerto Rico, and their fields were overlapping of a microbiologist and a structural biologist chemist, type of thing. And their collaboration proved to be very successful, even though it was transatlantic. Okay, and this is again just gives you an idea that she was a free living soul, so to speak, and just walking past the Pasteur Institute, she was inspired at age 12 to work in microbiology, and she's a true European nomad. She has worked at almost 12 different institutions all over Europe and US, just from Vienna to various places in the US, to Sweden, and now somewhere in Germany. Okay, and it's the two people are totally different personalities, but somehow their collaboration, along with their postdocs who did a lot of the hard work, had been successful in coming to the finding that you need both these types of RNA sequences to work as a joint. One by itself is not sufficient to work as an effective DNA editing tool. So that was their big contribution. Carpentier had discovered tracer RNA. Jennifer Doudna's lab had combined these two with hydrogen bonds and made something called a guide RNA. And so that became relatively very simple to chop the DNA and give a very effective tool for DNA editing. Okay, I'm sorry, this slide. And this is, again, this shows the reduction science to the maximum approach. This is almost blows your mind. This was a Japanese group that did published a study on actually photographing CRISPR with something called high-speed atomic force microscopy. I mean, to visualize the real space, real-time dynamics of CRISPR-Cas in action, okay? And as to how it is, the protein is unfolded, and this is the DNA strand that goes, this plays too fast, so you're not gonna be able to see it, type of thing. You have to really, this works at a nanoseconds type of speed, type of thing, okay? So, and this was almost a mind-blowing picture type of thing. So this is the DNA strand and the CRISPR, and again, these are the freeze frame pictures. So it was just an amazing piece of, work that was done. So you can say that you have seen, the real DNA molecule that was photographed at atomic level images type of thing. Okay, and so, and here what happens is that it indicates, it adopts the, it conforms, because as the biologist, you know that proteins has conformational changes, and so it forms a stable two-lobe structure, and along with allowing the DNA to go through things, so, and makes the fragments. Okay, and these are just the same images, in freeze frame. So I copied from their paper. So it's really an amazing piece of, technology use. Okay, and similarly, some of the other people who deserve credit also to working in Jennifer's lab, there are various bacteriologists who did the sequences and structure. The one guy was a microbiologist, another guy was a structural biochemist. And so their collaboration, worked out, to come up with this whole product, that how simple it was. And again, this just shows as to how adaptive immunity, we already showed you that slide in the first video. Okay, so we're moving right along. Okay, and there's not just one CRISPR protein, there are varieties of protein, they're classified, like type 1 and type 2. It gets fairly complicated, and the most common one that is being used is Cas9 that works on DNA. There are some other Cas proteins that work on RNA as well that are being used. Okay, so there are varieties of, it's a lot more, they're like, by the present time, there are like 36 varieties of subtypes between two types of proteins that have been discovered by various people. Okay, I think I'm going to skip this for sake of time. This is something called, this is a video on something called PAM sequence, because it needs almost like an identification for CAT to work. And the PAM abbreviation means is, the gaps that we showed along with the CRISPR sequence are called spacer sequences. And on front of that, it's almost like an ID card that you'd use. It's called a protospacer, adjacent motif. I mean, it's a small base pair sequence. It's like a check-in ID that you show to get inside a club or something, And so that's what, that is required. And the Cas protein goes through that in extremely fast speed through all these 3 billion sequences to identify to where it should be cut. That just blows your mind as to how fast this protein can, remember, DNA is all entangled. It's not wrapped in a nice laid out like a rope in your gym, okay? But it goes, this protein goes through this huge sequences and tries to identify this particular sequence. It's almost, which is a small sequence, and checks it. Okay, this is where you get cut. So it's like in a crowded club, a bouncer trying to identify you. Yep, you're the bad guy. I threw you out last time. So that's where it goes, so to speak. So that's the analogy I thought about. So it targets it. It's an essential targeting component which distinguishes between self and non-self. So it, so it again, so it is, so that's an amazing piece of evolutionary, warfare, so to speak. Okay. So, but it just explains to you what this PAM sequence is, type thing. It's
what is the PAM? A CRISPR whiteboard lesson presented by the IGI.
Okay, I think I'm going to skip that because it's, we have a lot more interesting stuff. And so this is And this, interestingly, as happens in science, a lot of people are doing simultaneous work. And as the Americans and the Carpenter were working, there was also a Lithuanian scientist who was a microbiologist who was working simultaneously. I think I'm going to butcher his name, Virginus Sixnis, okay. And he was working on the same this thing, and at the same time, and unfortunately, his paper, which was published, was rejected earlier by Nature, and he published in a different journal. And that paper was reviewed by the expert, which happened to be Jennifer Doudna. Okay, so that again, may have, there is some controversies as to that, give her the, just like similar to we have talked about in evolution, as to Darwin, sat on his work for 40 years. And when finally Wallace from Indonesia sent the same principle, that's when his friend decided, yeah, you better publish this. So this may have pushed Jennifer's group at Berkeley to rush and push. And obviously, the Berkeley has a lot bigger name. And so her paper was, published a few days earlier before the Lithuanian groups. Okay. And again, to the Nobel winners' credit, that their paper did not have clear-cut definition of what the tracer RNA this thing. So they were missing. And finally, at the big conference, these two papers were published, presented back to back. So again, whether she had some inside information or not, that gave her the incentive to go after to get the paper published, but and science, a lot of time, there is no prize for getting second. And this was the famous paper that you can see from Martin Janek, was her postdoc, okay, and she was the postdoc working with Emmanuel Carpentier, and these are the final two PIs. So this was the paper that won them the Nobel Prize, the programmable dual RNA guided DNA nucleus in adaptive bacterial immunity. And so it showed, they, again, just like Watson and Crick had said, it has come to our attention that this may be a way. So final statement, they said we may be able to identify genetic code when they did the DNA sequence. Again, it's interestingly how science is, that this was published in 2012, but still, that wasn't the biggest discovery of the science. The biggest breakthrough of this year was something in physics called Higgs boson, okay, which again later on was awarded with Nobel Prize. So CRISPR wasn't way up there on the list, So it waited until 3 years for the community at large to wake up that, hey, this is a dramatic discovery. Okay, and again, so then there's even more controversy with the East Coast and West Coast, and the earlier pioneer of genomic research, Eric Lander, who is the head professor at MIT, was the science director of Biden administration, and is a head of the Broad Institute at which is a deep-pocketed institute in Cambridge. So he wrote the paper about globalization of science, pointing out as to how many people were involved in the research of discovery of CRISPR. So this was a very it was very factful paper, but the science community in general thought that he was downplaying the role that Jennifer and Carpentier had played. And he may have had some ulterior motive, because one of his protege, who we'll talk about a little later, had done work in eukaryotes. Because let's emphasize that the work that the two Nobel winners had done was done in prokaryotes. And it was a lot easier to edit, DNA inside bacteria, which is not nicely protected by the nucleus. But they had no experience with working with eukaryotes, where the DNA is nicely guarded. So in other words, to edit a book which you cannot take home, it was a lot harder, than the book that you can just copy and take it home and read at convenience. To give the analogy of the difference between prokaryotes and eukaryotes, because the DNA is nicely guarded. So that's where the work of the Broad Institute researchers, was a lot more challenging. Okay. All right, I think another 5 minutes and we'll just take a break. I think it was 1:55, so we are moving right along. So this was one of the, Eric Lander, was trying to put things in proper perspective, but apparently a lot of the women scientists and some of the other people who were supporters of Jennifer, thought that he was downplaying their role. Okay, and he was criticized as, okay, I mean, this is like, a hatchet job, so to speak, and he was criticized. But obviously, so there was like a storm in the teacup or like a bad tweet type of thing. So, but it was a big scandal of his article, and he may have some ulterior motive to promote the Broad Institute work, or he may be genuinely motivated that it was a lot more challenging. We'll never know for truth as to where the truth was. Okay. Okay. All right. Let's see. I think I just put this in. This is summarizes it. This is a video that summarizes all that I was harming about with a nice cartoon. This is a video from University of Singapore, and they do some excellent work. So I'll let this play.
What does it take to invent the next iPhone? Or find the next penicillin? Does it take a genius like Steve Jobs or Alexander Fleming, who in their garage or isolated laboratory had an eureka moment and magically discovered the next big thing? What is the formula to discovering the next breakthrough? It all begins with observation. In 1987, when a group of Japanese scientists discovered an odd DNA sequence in a type of bacteria, the E. coli. These repeated sequences were something that had never been seen before. They are palindromic, meaning they read identically forwards and backwards for about 30 bases, and are separated by spaces of roughly 36 bases that are not palindromic in nature. None of the Japanese scientists were able to elucidate the purpose of these sequences. Surrendering, they simply reported the existence of the sequences and concluded the study. Some years later, in 1990, Francisco Mojica chanced upon the same palindromic sequences when he was studying other classes of single-cellular organism, the archaea. They are cousins of bacteria that look similar, but have very different genetic heritage, and thus biochemistry. Like any good scientist, Mojica consulted scientific literature and saw the Japanese scientists' findings. Excitedly, Mojica posited that for the same palindromic sequences to be present in both archaea and bacteria, the sequences must serve an important purpose. He named the sequences CRISPR, clustered regularly interspaced short palindromic repeats. Focusing on the spaces, Mojica painstakingly extracted each spacer and inserted them into a bioinformatic analysis tool called BLAST, the basic local alignment search tool, hoping to identify these spaces with other known DNA sequences. Perseverance eventually paid off. The spaces were indeed a match with DNA sequences belonging to viruses. Why would viral DNA end up inside bacteria? Mojica hypothesized that these spaces encoded instructions for an immune system to protect the bacteria against these viruses. Meanwhile, in 2006, the continued discovery of CRISPR took place in a yogurt production factory that was facing a serious problem. The cultures used to produce yogurt were often attacked by viruses, causing the cultures to fail. A young scientist named Philip Horvath decided to solve the problem. He observed that certain strains of bacteria used in the cultures were immune to viral attacks, while some other strains could not protect themselves. The resistance was not due to cell membrane mutation, but was due to virus DNA sequence within the CRISPR of the resistant bacteria. Horvath carried out a series of experiments that added virus DNA segments into that CRISPR array of non-resistant bacteria that proved the hypothesis that CRISPR was indeed an adaptive immune system, a kind of vaccination for the bacteria against the virus, and that immunity depended on a precise DNA match between the spacer and the target virus. Going further, he identified a gene in front of the palindromic repeats that coded for a protein enzyme called Cas9, which is responsible for cutting virus DNA and hence granting immunity. 1 year later, John van der Woest jumped onto the CRISPR bandwagon. He was the first to create artificial CRISPR arrays, meaning that he could program the CRISPR-based immunity directly with any combination of DNA sequence and instruct the CRISPR system to protect the bacteria against any viruses. In this way, he demonstrated the first case of directly programmable CRISPR-based immunity, an artificial flu shot for bacteria. Adding on, some years later, Emmanuelle Charpentier established the full mechanism of CRISPR. She accidentally discovered the last essential component of the CRISPR system, trans-activating CRISPR RNA, or tracer RNA, which has an important role in the maturation of the precursor cRNA into the cRNA. Hence, in 2012, the field had reached a significant milestone. The 3 necessary and sufficient components of CRISPR were now known, and the discovery was made. By 2013, CRISPR had become a rising star in the scientific field, and many scientists began studying it, accelerating the process of tinkering and application with CRISPR. Virginius Schixners successfully moved the CRISPR system from inside the bacteria, in vivo, to a test tube environment, in vitro, while Emmanuelle Charpentier and Jennifer Doudna focused on optimizing the natural pathway and artificially created single-guide RNA, or sgRNA, which substitutes the function of tracer RNA and cRNA. Now that we know how CRISPR works, scientists began working on CRISPR's real-world applications, gene editing. Several scientists worked on this, but the results were merely modest. In 2013, Feng Zhang and George Church came.
Okay, I think, I'm sorry, let's finish that. I'll be talking about that in a few minutes, so I think this, otherwise, just, let's take a few minutes break and then we'll continue talking. I'll pause the recording and see you in 5 minutes. Resume recording. And all right, so I think we have badmouthed, my favorite scientist, Eric Lender, enough, and I just feel bad for him that he got such a bad rep type of thing, and part of it was that all the women scientists ganged up on him, and saying, okay, well, you want your boy to get the Nobel Prize, so, but enough of this, things, about how he was called the evil genius of MIT, so to speak, and so we'll, but that will stay away from all the things, we're not, and again, so this was the Nobel winners dispute, because, okay, moving on to Feng Zheng, who is, who worked on optogenetics, and if you have never heard the word, look up, because I think this is the green fluorescent proteins, as to how controlling its cellular activity with light, So it's there's a well-known guy, who moved from Stanford to Harvard, named Carl Dassaroff, and they have done a lot of work on optogenetics, So how they can, without having to put wires inside, they can control the movement of the nerve cells and other stuff with a laser lights alone. So it's a brave new field. So based on that, he was familiar with how to get the CRISPR molecule, inside the nucleus. So something called electroporation. Okay, I'm not going to get too much into it. I had a whole video, but I think we just don't have that much time to go into it. But he was familiar with it. So now, unfortunately, he did his PhD with George Church, and he was working on his own at the Broad Institute across the street at MIT. So that was considered, oh no, not cricket in the science field, and then he finished, finally he published, oh, by the way, we have finished this work, he didn't tell George Church, and neither, and didn't tell Jennifer either, type of thing. So that's why he was considered, so okay, well, he was trying to run to the finish on his own, and so that was considered, not gentlemanly, but that was, and they all, now unfortunately, this is the big thing, that unlike the days of polio vaccine, all these people, including her first postdoc, they all wanted to start companies, and pretty soon, they all got together and started a company. But again, so like either for whatever reasons, she did not enjoy working with East Coast people, that they were more pushy and went and started her own company. So you can see the varieties of names, because there are huge, and all the universities are also wanted to patent this, and the court and from the patent office went to the courts, and finally, a Broad Institute got the patent for eukaryote editing type of thing, while Jennifer and Carpentier got the patent for the technology itself. But it was a different mess in Europe. So it's it's an amazing thing as to who is going to benefit more from this, type of thing. So it's it's a big legal and hassle type of thing, and the lawyers have gotten rich from working for all these universities and private companies. Okay, all right, and then again, so they were recognized, and as I mentioned earlier, that they don't like to give Nobel Prize to 4 people, because the eukaryotes, that is the cells with nucleus paper, was published back to back by George Church, who's sort of the grandfather of molecular biology, and Feng Zhang. Okay, and at the same time, these 2 ladies, so that's how the prize just went, and maybe so we'll never know as to what was in the minds of the gnomes in Sweden. So okay, so but they were, so we already, I showed you this slide, but there was basically, so this is gene editing. Okay, so we'll get more into it. So now these are some of the ethical things that gene editing and other stuff that were done. And this is a slide from Matthew Cobbs, who talks about the genetic age type of thing. So what if, okay, so now just think about all these individual statements. What if a cancer-causing virus was inserted into E. coli gut bacteria? How the DNA would be passed without idea of what would happen? A virus more transmissible. What if science wanted to edit human embryo and implant them? So these are all hypothetical scenario, So does anybody want to see what they feel about it? All these things? Okay. I mean, are they, would you be comfortable with all these propositions, type of thing? Okay. Anyway, for the sake of time, we would say all these are not just if or hypothetical situations, they've all happened. Okay, type of thing. So this is, we talked about earlier, that started the race between Paul Berg in 1973, where her postdoc wanted to introduce a cancer-causing simian virus into E. coli, and that started the first Asilomar conference type of thing. So, and then again, this is highly pathogenic virus that is called, the study is called gain of function, by the way. Okay, so they make the virus, like a more transmissible by air, type of thing, instead of just contact. Okay, and the edit human embryo was a big scandal that occurred in 2018 by a Chinese scientist who edited the germline embryo, because supposedly there was, everybody had agreed that we will not edit germline, because if you edit the X and the sex chromosomes, that is there for all sequences forever. So that's why people had said it had a self-imposed moratorium in sometime in 2015, when the big molecular scientists agreed that they will not work on editing germline type of thing. It's okay to work on other things, but not on this. But then some Chinese group had worked on non-implantable embryos, and while the man who worked on it, he actually went ahead and did that, and that is, we'll talk more about it as we go along. Okay, so this is again, so and just to put things in proper perspective, nature has been editing genomes for a long time. That is, like this is, the basic, corn, has changed from here to here type of thing. Is a much more useful type of thing. Darwin's finches have evolved their beaks. Okay, and the knockout mouse, which we talked about, which was done with homologous repair type of thing, and that was done as far back as 1980s. Okay, so it's not a new procedure, basically, type of thing. So, and this was done, and those were Nobel winners, who did that, work on mouse blastocysts, and were able to knock out certain genes, and create a useful mouse for doing cancer research. And it is used by thousands of labs, and That is the first time the mouse has been patented. And I showed you the picture from the first class or something on the Harvard knockout mouse. So it's not, and the gene editing is, like it's a big news in all, just not just professional journals, but all that, but even just in popular press, including Time and Newsweek magazine has made headlines type of thing. So it's like, okay. And so it's, it has written the zeitgeist, so to speak, So, and it has made it to movies and TV shows, and we already talked about that, even before CRISPR and gene editing, people, starting from the early days of bacteriological warfare, which was banned earlier during the Second World War type of thing, that the Russians were secretively doing, two scientists named Bev and Ovchinnikov were appealing to the communist regime to use genetics for bioweapons. And they had done some, some really scary work, about fusing various proteins against plague bacillus, making anthrax more pathogenic and transmissible. And they also had their share of accident, that about 64 people had died due to leak in their biological establishment, Sverdlovsk. Okay, and then again, so they were really, and after the collapse of Soviet Union, they just that some of the facts were coming out. So this was, and some of them were actually invited to the Asilomar conference, by the way. Okay, and at that time, the U.S. people just looked down upon, oh, the Russians, they don't know anything, but they were far ahead in biological warfare than you realize. And even just to rub in to this thing, even Winston Churchill wanted to purchase, actually put it in, wanted to buy anthrax bombs, during the war. So we were not, and the U.S. military has a huge research base, in somewhere in Maryland. I think I forget the name, Fort something, sorry about that, and so this is, and again, after the Al Qaeda and this thing, that the budget for biological warfare has been increased dramatically. If you remember that shortly after 9/11, one of the employees of NIH had sent envelopes to various political leaders, and then he committed suicide or something like that, if I recall. Okay, so this is, and so this again, at the same time, the varieties of other researchers have had their share, even in the West, type of things that, and after 9/11, it really got big expansion in funding, type of thing. So, and again, there was the Japanese group, then Shirinoko was released the bug in the Tokyo subway. Luckily, it didn't cause too much of a problem, but it, so, and similarly, there was a fringe group in Oregon, and who had released salmonella, in one of the small towns in Oregon. So biological warfare is a real possibility type of thing. So, and again, we've all lived with that, with the viruses, so I won't dwell too much into it. And this was a repeat, right? Sorry, I should have. Okay. And so again, so there was similarly other scientists, said they've done, they realized they've done something stupid, basically H5N1, which is bad enough as it is, they've become more transmissible type of thing. So it's a so-called gain of, now it remains to be seen as to whether it is worthwhile studying this so that the other countries won't get a leg up on you or not. Okay. So this is, some of the research might still be going on that we will never know for sure. Okay. And again, so for the role of CAR-T therapy, this has been the big Nobel Prize in medicine. Okay. A chimeric antigen replacement therapy. And this was used initially, it was easier for using for hematological cancer. And this was the poster child of that.
I really only remember like the fun things like playing air hockey with my dad or doing things like that. So, I mean, occasionally I'll have to ask like, when did this happen or when did we do this? Because I'm sure that my parents remember everything.
Emily was diagnosed when she was 5 years old with acute lymphoblastic leukemia. And they told us that it's the most common type of childhood cancer and also the most treatable. But once you relapse more than once, like Emily did, there are fewer options to treat that. It got to the point to where they said, here we don't have any more options for her, and we think it's time for you to take her home, and she'll have a couple of weeks left. We just looked at each other and said, we have to call CHOP.
At that point in time, her treating doctors are saying the only option for a patient in this situation is hospice. Family didn't want that answer, and by an amazing series of events, this CAR T trial opened at the exact moment that she needed it.
We know how close we were to losing her, but finding something outside the box that was a little bit different gave us hope. Dr. Grupp was up front saying we don't know what's going to happen.
But we knew that we were surrounded by a great team who just wanted to help Emily. And, you know, if we try this and it doesn't work, we know that we did try everything that was out there. We did everything we possibly could.
Over the next 24 hours, that was the scariest part of her treatment. Those cells killing the cancer so fast overwhelmed her system, and things just kept getting worse.
She got so sick that we didn't think she was going to make it. We identified a number of these proteins that were unbelievably high, but one of them was actually a protein that we had a drug for. We gave her that drug, and that changed everything.
She woke up actually on her 7th birthday on May 2nd of 2012, and then they tested her. Dr. Grupp said to me, "This is amazing. We don't see any cancer."
You know, we just thought, let's see what happens.
Okay, so she's alive 10 years later. So that's the thing. She was the first pediatric patient to receive chimeric T-cell therapy for cancer. So that was one of the few success stories. And it's been done many times now. Okay, and so again, you know, so this is kind of a more busy slide about the role of, you know, genetic variants. Remember, we talked about in the earlier as the Mendelian base of diseases. You know, there are like 7,000 diseases. A lot of them, you know, are done with something called transition point mutation. That means one letter this thing, and there are varieties of deletions and this thing. So a lot of these are actually treatable. Thing, and the Boston group is working on a rather rare disease, you know, called progeria, where you know the body has a problem with the protein called laminar protein, and the child just ages very rapidly, type of thing. So they're working on, you know, modifying the particular protein, you know, with one letter is changing from G to T in the genetic sequence. And similarly, this is an example of sickle cell, where again, you know, you're changing letter A to T, okay? And so this would be, you know, a way to try to cure the, you know, Mendelian basis, you know, where similarly, some of the diseases in cystic fibrosis and Huntington's disease, you know, so these are the targets that people are aiming for, so to speak, you know, by something called, this is even one step further than the CRISPR-Cas, that not just altering or cutting out a gene, but changing the whole base, you know, from A to T. I think it's called base replacement therapy, and I'll talk more about it as we go along, type of thing. So, okay, because with the CRISPR, sometimes, you know, the healing process, the natural healing process is something different, that it can cause unexpected, you know, insertions and deletions. So it's not as foolproof as one would like, type of thing. But the base editing give the people who are doing the editing work a lot more control. And so that's the next evolutionary step in the treatment of some of these diseases. Okay, and so again, so these are the ways with, you know, the nature tries to heal the DNA repair. You know, the quickest one is something called non-homologous. Means it's just like I was thinking about how to explain this. It's just like putting in a Band-Aid on it, type of thing. Doesn't matter whether it matches, the two ends match perfectly or not. Which is the quick and dirty repair, so to speak. That's why the fancy word that they use is called non-homologous end joint repair. While the homologous is trying to match, like the zipper threads or teeth matching perfectly and aligning. So that's the homologous, but that's much more time-consuming type of thing. So initially, because by default mechanism is the non-homologous, and so that can leave some defects which are undesirable. So that's why it's how the healing process takes place. With the CRISPR-Cas is important as to how. Okay, and again, as we talked about now, people have moved further away from CRISPR, and this is what we call. This is done by another brilliant Chinese American scientist at Harvard. That thing. So he's a colorful character type of thing. That he was one of the first person who got his PhD at Harvard, and his work was so exemplary that he did not have to go through the usual process of postdoc. Okay, which most of the time, most of the PhD people, as you know, go through at least 4 years of, heartbreaking postdoc work. Well, he was given assistant professorship at ripe age of 29, and then within a few years, he was promoted to full professorship. At the same time, just on the sidekick, his amazing teacher, I think he was, obviously, and at the same time, he has taken his students on card counting trips to Las Vegas. So it's a colorful character, to put it mildly, type of thing. So, okay. But he has, they've come up with the varieties of procedures called base editing, which is, there are varieties of, DM enzymes that are used to replace the, and I think that I can send, for those of you who want to see, I can send out the videos, but this is replacing the genetic code, basically, from one to the other directly. And so these are the point mutations are done. So this avoids the hassle of double-stranded break, okay, type of thing. So that way it avoids the faulty insertions and deletions that could take place. And that work was done by his postdocs at David Liu's lab, okay. And then further on, they've even gone to something called prime editing, which I think which again, similarly, it avoids the hassle of double-stranded break, because what it does is deactivates the Cas protein completely, so to speak. And so it does not make this full, so it's a lot more effective in doing multiple point addition at the same time, okay? So it allows, without generating these breaks that they were worried about, type of thing. So, and okay, and so this can be very useful for conditions such as various hemoglobinopathies, okay. And then again, at the break time we were talking about that they've also done as to taken a page from evolution itself, and they've created a process of something called phage-assisted evolution. So they can replicate what has taken weeks and weeks for natural evolution to take place in within less than 24 hours. So that is the way of studying how the proteins would change. Okay, so those are some of their cutting edge technologies that they've worked on. Okay, okay, and again, so that the warfare inside the bacteria and phage goes on. That there is also something, it's like phages attack a bacteria, and bacteria have developed immunity. But then phages have come up with something called anti-CRISPR. Okay, so that again, so it blocks the so that the warfare between the major species just continues, type of thing. So, okay, all right, okay. So this is again a little bit more video that again, so anything sells better with a British accent.
Immune system. CRISPR-Cas9 has been adapted into a powerful tool for genomic research. There are two components to the system: a DNA cutting protein called Cas9 and an RNA molecule known as the guide RNA. Bound together, they form a complex that can identify and cut specific sections of DNA. First, Cas9 has to locate and bind to a common sequence in the genome called a PAM. Once the PAM is bound, the guide RNA unwinds part of the double helix. The RNA strand is designed to match and bind a particular sequence in the DNA. Once it's found the correct sequence, Cas9 can cut the DNA. Its two nuclease domains each make a nick, leading to a double-strand break. Although the cell will try to repair this break, the fixing process is error-prone and often inadvertently introduces mutations that disable the gene. This makes CRISPR a great tool for knocking out specific genes. But making double-strand breaks isn't all CRISPR can do. Some researchers are deactivating one or both of Cas9's cutting domains and fusing new enzymes onto the protein. Cas9 can then be used to transport those enzymes to a specific DNA sequence. In one example, Cas9 is fused to an enzyme, a deaminase, which mutates specific DNA bases, eventually replacing cytidine with thymidine. This kind of precise gene editing means you could turn a disease-causing mutation into a healthy version of the gene, or introduce a stop codon at a specific place. But it's not all about gene editing. Several labs have been working on ways to use CRISPR to promote gene transcription. They do this by deactivating Cas9 completely, so it can no longer cut DNA. Instead, transcriptional activators are added to the Cas9 by either fusing them directly or via a string of peptides. Alternatively, the activators can be recruited to the guide RNA instead. These activators recruit the cell's transcription machinery, bringing RNA polymerase and other factors to the target, and increasing transcription of that gene. The same principle applies to gene silencing. A CRAB domain fused to the Cas9 inactivates transcription by recruiting more factors that physically block the gene. A more outside-the-box idea for using CRISPR is to attach fluorescent proteins to the complex, so you can see where particular DNA sequences are found in the cell. This could be useful for things like visualizing the 3D architecture of the genome, or to paint an entire chromosome and follow its position in the nucleus. CRISPR has already changed the face of research, but these new ideas show that what's been achieved so far could just be the tip of the iceberg when it comes to CRISPR's potential. Whatever comes next, it seems the CRISPR revolution system.
Okay, so this is, again, so there are more of the stuff, but we already, just for the sake of time, we won't get too much into it. Okay, now, again, the more important thing, because as we said earlier, you may recall, that most of the common diseases involves hundreds of genes, if not thousands, like such as schizophrenia and diabetes. So they're not going to be that easily treatable. But the where the CRISPR will shine in increasing, in agriculture and botany and other sciences, and along with, obviously, so it will have a role in more in agriculture thing, diagnosis, and also, last but not the least, in treatment. So we'll cover each of them in a few of the next slides. So again, so these are the varieties of ways that we already could put it in the introduction slide: agriculture, and programmable targeting, and getting rid of mosquitoes, like we talked about for gene drive screening for drugs, type of thing. So, and again, we've talked about a little bit about organoids. So these are the varieties of ways it will have use. And when it is combined with stem cells research, that's where the big thrust will lie, because it gives the scientists, normally otherwise it is a lot more difficult to create an isolated stem cell line from your own liver or from your own muscle, so to speak. But with CRISPR, it's a lot easier to create your own particularly dedicated cell line. So when you combine these two technologies, it makes it a lot more easier, to do research and find ideal therapy for that particular pathology that we may be dealing with. So reprogramming induced pluripotent cells has become a lot more easier. And again, remember we said about genome analysis that so many times, we just came up with VUS, means variants of unknown significance. So that is where doing the research on the individual cell lines from your own genomes, well, it's going to be a lot more useful to see what this particular variation actually means, type of thing. So this would give a lot bigger tool, for doing research, not just like in vitro, means outside, and then that would give us a chance to do, give therapy in vivo, means injectable therapy or choice small molecule drug. And last but not the least, when you get the sequences, you can compare it with other sequences that are available. So you can see where else in other cell lines it has occurred, So that research is called in silico, means comparing huge chunks of data with bioinformatics. So there are varieties of ways these new groundbreaking technologies will be combined, type of thing. So, and this is just an example. We talked about, this is the attractive use of edited T cell therapy and with individualized for malignancy, and so-called personalized or precision medicine. I think some of you were in the class of mini medical school, and we talked it. So those are some of the ways in which so-called bespoke personalized therapy can be devised. But again, so these are extremely labor-intensive and expensive, to put it mildly, type of thing. So, and they're gone after some of the other easily common but inherited diseases, not necessarily malignancy. There's a type of blindness that labors congenital blindness, amaurosis. And for that, some of the drugs that were devised, but not all of them have, panned out, because some of the drug companies have decided to get out of business. Now, those of you who watch late night TV, you may have seen ad that call your doctor if you have tingling or numbness or have heart failure. And I think what the companies are trying to do is that there is a rare cardiomyopathy, this heart muscle weakness called cardiomyopathy, and which is, occurs more commonly due to degenerative protein formation called amyloidosis. But one particular rare type is called hereditary transthyretin amyloidosis, which can be fatal which is done with single DNA letter abnormalities. So, and again, it's like, out of so many mutations that take place, this is relatively very small percentage. But I think the drug companies are trying to drum up more business by trying to identify cases, which may have been, and physicians may not think, oh, it's rare, it's not worth checking for it right now. So they're encouraging you to, there's a company called Innovative Genomics, so, and their drug was approved, type of thing, by the way. So those are because I had to almost think about it. So why are they putting this nerve blindness? And so then I thought about it, I looked it up and said, okay, wow, this is because usually you don't see, they don't name any drug actually with it, because that is the expensive gene therapy that they are promoting, basically. Okay. And again, this is, this list I just did it for you can look at it if you're interested. These are the trials that are going on with CRISPR, and the ones that are in yellow are for cancer. The others are for other rarer diseases. Some are for infection, some are for blindness. As we talked about, type of thing. But a couple of them for thalassemia. Some are for HIV. Others were recruiting. So this is a fairly recent slide from medical school out of Delaware. Okay, and so this, but again, so these are all still remains how they will pan out, type of thing. So, okay, excuse me. I'll call you back. I'll call you back later. I'm teaching. Yeah, I'll call you back later. Yeah. Okay. Yeah. So this is, sorry about that. Yeah. So these are some of the trials that are going on as to how many of this will be successful or not. Because recently one of the companies that Jennifer and Fang Zhang were involved, Editas, they had some setbacks. So they recruited, they dropped their trial because they thought they were able to modify this blindness gene, but their success rate was far less, instead of, expecting 8 out of 10, their success rate was only 2 out of 10. So they dropped the trial, so it may not be as straightforward as we think. So, so the jury's out on it yet, okay. And again, so this is, we have said about, how the knockout mouse and, this may be a duplication type of thing, but it talks about the various cell-based therapies. And we already talked about the amyloidosis, which is type of thing. Okay. Okay. And again, some of the, this was, I think, in fact, Mr. Kevin Chittum had talked to me about this, that this was, a paper that just came out, fairly recently type of thing, and they're talking about phase 1 therapy, about taking only a certain amount of mutations in cancer patients, like there are huge number of mutations that occur in malignancy cell, but they selected out based on sophisticated data analysis, certain genes, and they tried to see whether re-engineer immune cells called T cells and introduce them into the patients with refractory cancers. And their data it was almost like a phase 1 trial. So at least they didn't get it sick and their malignancy stabilized. So that's a very early preliminary data. But again, as I keep repeating myself, but this is going to be a very expensive, it's almost going to be like a needle in the haystack, that if you may recall that cancer cells can have huge number of mutations as to see which ones one should pick out, that's going to be a challenge. And as to how they will respond, that time will tell. Okay. So this is, this was what their idea as to how they were taking the normal T cell, doing the CRISPR thing and modifying and attaching them to a lentivirus vector and re-injecting them, so to speak, and so this is so-called exogenous cell therapy, or like it's done outside the body type of thing. So this way there is a hope that it can be mass manufactured, reducing the cost. Because if you try to do something called personalized, it becomes, first of all, time consuming and very expensive, to say the least. And there are varieties of therapies have been approved. The names are, and some of them have been approved for lymphocytic leukemias and varieties of hematologic cancer, a rare blood tumor called multiple myeloma. Okay, so those have been approved. Again, but I'll give you some data about the cost of these as we go along. Okay, and so again, so this was an article. This is a slide from NPR website, type of thing. Okay, so these are some of the success stories, type of thing, that this was a person who was born with a mutation causing the one that I talked about, Leber's congenital amaurosis. Okay, and he was totally blind, and this was a successful outcome. He was able to, regain his vision, type of thing. And then again, similarly, somebody had abnormalities with color blindness that was successfully treated with CRISPR. Okay, and the most successful person is one that made a story on 60 Minutes, a young woman named Victoria Gray, who had a really rip-roaring sickle cell disease, and she was one of the first patients. Was done, I want to say either Texas or Tennessee, okay, and to receive CRISPR gene editing therapy, and she's obviously, for the first time in 20 or 30 years, she's been free of sickle cell crisis. So you can see that it is slow but steadily, making headways into this thing. So there is hope for some of the so-called low-hanging fruit that one can attach. So these are the 3 individual stories that are published on NPR website. Okay, and again, so this is again, we talked about, and there are other people have also been, done. So this was the paper finally in New England Journal about, the CRISPR edited therapy for sickle cell disease, type thing. So, okay, and again, we talked, this is much more interesting because, again, as I mentioned earlier, that transthyretin amyloidosis is rather rare illness type of thing. So they won't have that much of a market, even though they are okay. But high cholesterol gene is very common as to the homozygous, means both parents, so these are the patients who have cholesterol of 400 to 500, okay, and they have abnormalities, genetic abnormalities, there's things. So a first trial is done by the Boston group in elsewhere outside the United States, so modifying this particular gene, to lower cholesterol. And they've seen some good results. So the trial, if that pans out, that is going to be a big, advanced type of thing as to, okay, and for cholesterol lowering type of thing, okay. And so this, again, so this is again the cartoon about showing as to how the cholesterol manufacturing takes place type thing. So, and so that trial may be something that may be a money-making business and may again help a lot more people than you realize. So that is done by the Boston group, about, because you may have heard about that people who cannot tolerate statins are taking injectable drug once or twice a month, to modify this particular enzyme in your liver, okay. So if this gene therapy works, that may stop the need for this particular, intravenous drug therapy, which is not cheap by itself, okay. And again, we've already talked about sickle cell disease, so that may be one of the, so, and the earliest thing. So, okay, and yeah, we've already talked about the SCID trial that was done, and somehow due to the way the community is, Navajo Indian community has a lot more higher incidence of combined immune deficiency syndrome. So the California UCSF group is working on this particularly a disadvantaged group for severe, because remember I talked about earlier that the trial was dropped. So state of California and UCSF are working with a special institute called Regenerative Medicine, which with the help from FDA to do the gene trial for in this particular Native American community who have a lot higher incidence of gene abnormalities, in that particular group. So that's about as hot off the press as you can do. Again, going on to the food type of thing, CRISPR-Cas, has been to make a tomato a lot more, first of all, larger tomato, better tasting, increasing fruit size, and at the same time, giving a tomato a facility to improve a vitamin D inside tomato. So those are some of the uses. So tomato may be one of, now this may be more acceptable to the GMO community because you're not introducing, a new foreign gene, you're just modifying the particular genes type of thing. So that may be more acceptable type of thing, and it may not have to go through the lot of regulations that have gone through. And again, a lot of the monocrop bananas are called Cavendish bananas, and they're attacked by a various fungus, and that is almost going to be a disaster on the banana industry type of thing. So some of the researchers and especially the farmers in Australia are working on this particular gene modifying bacteria to save the banana crop, because otherwise you're going to have some serious trouble with banana crop, because this is one of the few hardy bananas that is grown all over the world type of thing. So last but not the least, as I mentioned earlier before we got started, that some of the agriculture geneticists are working on eliminating the gliadin interacting genes from wheat. So that would help the people who have gluten enteropathy. So that is one way to improve, and also to make wheat a lot more rot resistance, because that's another problem that the red rot, the fungal disease, can damage the wheat crop. So that is one way CRISPR may be able to improve the fruit crop and feed the bird. So a lot of the plant geneticists are working on trying to improve the fruit supply for the growing bird population. So these are some of the areas where CRISPR may be a lot more useful than for treating so-called chronic diseases such as diabetes or, schizophrenia, I think. And again, it has been for diagnosis in the field, it has been a dramatic boon type of thing because it's a lot faster and cheaper than CRISPR. Okay, and it can, it can target sequences of various pathogens. And the same way this was used, very efficiently in sequencing the SARS-CoV virus. Okay, that even smaller countries such as Sub-Saharan Africa, they were able to go up and running with CRISPR lab, because to set up big PCR lab and the equipment was a lot more expensive and was beyond their reach. Okay, but they were able to go up and running and do sequence of the particular variant that they had. So this could be used in the field, so to speak, and appropriately some of this equipment that has been automated type of thing, and it's commercial detectors have been marketed. And they've been named Sherlock. I had a video for it, but I think just for time's sake, I think I can eliminate it then. Okay, and last but not the least, the scandal which hit the world in 2018 was the Yang Ku affair. That at the big meeting in Hong Kong, he announced that he had succeeded in modifying the germline of two girls. Because apparently in China, and his claim was that there's a lot of stigma to HIV, and people who have this particular mutations are resistant to HIV. So that's why he had tried to modify the germline cells and reimplanted the embryos. Okay, a lot of this abnormalities is done in some of the North Europeans have this genetic variation that protects them from infection. So and initially, he was praised by the Chinese government and his mentors in Texas as well. But when the big who's thought that his methods were a lot more sloppy, and not all the cells were as clearly modified as he thought. Okay, so the whole weight of the word, scientific community, and also the Chinese government was sensitive to Western criticism. So his hopes for being the first to do gene editing in germline and getting praises were dashed, and he was actually sent to prison in China for a couple of years now. And I don't know if he's been released yet or not, but again, so that was again. And but when you listen to the whole things that went on, obviously he was rushing and not as experienced as he thought he was. But at the same time, some of the criticism that because it was a good target to pick, if you listen to, and the scientific community in the West was also divided as to how they should approach. Some of the people thought that, it wasn't, the so-called red line has been crossed when the technology was released. Somebody was going to do it, and also, and then another more respected scientist in Russia is working on. Okay, actually, yeah. So this is the slide as to what he had done, but I think so. This was his announced the birth in 2018. Okay, and so this was the scandal that I already alluded to, type of thing. So, and again, not everybody agrees with the so-called moratorium type of thing. So, okay. So it remains to be seen. And this is just the slide. I had a whole video, but I did not put as to how easy it is to. That was easy for people to diagnose, very quickly, and make a diagnosis using CRISPR technology. And it was almost automated type of thing. It made it a lot easier for people to work rather than more complicated and time-consuming PCR. Okay. And again, when we saw the virus of unknown significance type of thing. So I've already talked more about it, but I think I'm going to go through some of these. Okay. Yeah. So, okay. So, and I mentioned earlier that Editas is halting the study because their study on Leber's blindness did not turn out to be as well as they thought it was going to be. So it will remain to be seen as to how successful other trials will be. Okay, and again, so this is some of the farm things. It may be much more useful. So there, CRISPR may have a bigger role. Okay, like frost-resistant plant to work with, and even generating biofuel. So that has varieties of rules, and other non-health related issues. Okay. And again, so it's unpredictable as to how it will come out because, it has taken 3 billion years of evolution, and we think that we're going to be able to modify that quickly is remains to be seen type of thing. Okay. So, and some of the ethicists have again, the ethicist community is equally divided. Instead of being pessimistic, saying that, okay, we are messing up our germline and the sacred human existence. But some people are saying that there is cautious optimism type of thing. And this was interesting that sex is for recreation, science is for procreation. So it may change that, we may be able to diagnose and prevent some of these diseases earlier. So it may be like, you would select out certain these things. So obviously it would have to be, regulated that as to how well. Okay. And again, we talked about the deaf community and even people who have, who have achondroplasia and short stature. They're saying, well, don't edit us out of the human existence type of thing. So there is a pushback from the deaf community as to saying, and apparently a scientist in Russia, a guy named Denis Rybakov, he's waiting for approval that he has 5 couples waiting for, because they're both deaf, and so they're waiting for, getting permission, to edit out this particular gene, which causes genetic abnormalities, modifying this particular gene in your inner ears. Okay, so that will remain to be seen as to whether he is given permission or whether he goes ahead and what are his outcomes. Okay. And so again, so these are some of the timeline guidelines, but it's just, okay. And this is worth saying, type of thing. So this is, David Letterman used to have 10, best.
CRISPR-Cas9 is a gene editing mechanism.
This guy talks even faster than I do, so he'll go through quickly.
Derived from a naturally occurring set of DNA sequences found in bacteria. While still in its infancy, the technology has garnered a lot of attention in the past few years due to its accuracy and flexibility, as well as its relatively low cost. You can even buy your own CRISPR kit for a few $100s and use it to modify DNA in almost any way possible. From pest-resistant crops to designer babies to permanently curing ailments like cancer, one can only imagine the things that can be done with a technology like that, especially in the hands of skilled researchers who know what they're doing. Number 10. Edit food. Improving yields and nutritional values of existing food crops is a major challenge of the future, owing to factors like climate change and an ever-growing human population. While CRISPR isn't the only technique aimed at solving it, it's one of the most promising, as it provides gene editing access for small and independent growers around the world. While it'll be a while before you start seeing entirely new fruits and vegetables made by CRISPR at your local supermarket, it's not too far into the future either. One can already buy some varieties of fruits and vegetables modified with CRISPR in some places around the world, with many more experimental varieties on the way. There are still some ethical issues around what should and shouldn't be edited, especially regarding more complex food sources like animals. To solve them, countries around the world are working on various types of regulations to oversee the gene editing of food, which should make it safer and more reliable for mass production and consumption. Number 9. Eradicate malaria. Malaria is one of the deadliest ongoing insect-borne diseases around the world, killing hundreds of thousands of people in an average year, especially in the high-risk tropical and subtropical regions of Africa. CRISPR provides one of the many permanent solutions to the problem, as it could be used to design something called a gene drive, which could then modify the entire mosquito gene pool to drop the disease altogether. Obviously, it's not as easy as it sounds, though early experiments have been promising. In a recent study, researchers from various institutions in the UK and Italy did something similar to a population of the mosquito species responsible for the highest number of cases in sub-Saharan Africa. The CRISPR modification resulted in the complete annihilation of the target group within a year, proving that it could be done. While it's still far from the complete eradication of the disease, as that would require replicating the experiment on a much larger scale, it's definitely a step in the right direction. Number 8. Biofuel. Coming up with clean, sustainable ways of generating energy would be a major problem in the future if it isn't already. Biofuels are a promising solution as they're naturally occurring and leave a minimal footprint on the environment. It's difficult to mass produce them though, especially at the scales of production we're talking about. CRISPR provides a possible fix as it allows researchers to come up with new ways of modifying the genome of natural biofuels. It's a growing area of research where multiple teams are looking at different ways of implementing the CRISPR protocol into the biofuel production process. Early experiments with some types of biofuels like microalgae have been successful, where researchers were able to change DNA of a few known microalgae species using CRISPR editing. Number 7. Camera One. Camera One is a new technology built by a team of scientists from Harvard and MIT. Using the CRISPR sequence, it modifies cells into a kind of black box recorder that can record changes at the DNA level, which could then be used to track the origins of a range of genetic features. Recording these variations in real time could one day allow us to understand the root causes of long-term diseases like cancer, as Camera One is perhaps the first technology that gives us a real-time window into the complete life cycle of a cell. The possibilities are endless, though much like all other CRISPR techniques right now, Camera One is still in its early stages. Like CRISPR, it could also be used as a base to build other applications in the future. Number 6. Detector. Like Camera, Detector uses CRISPR technology to come up with an entirely new application of its own. Designed as a detection tool for any kind of genetic information you feed into it, Detector could soon prove to be a revolutionary tool for the early detection of serious diseases. In one experiment, Detector was deployed to detect the HPV virus, a known possible cause for cervical cancer, among other random types of viral strains, and it proved to be quite good at it. The same technique could be further developed to detect the early stages of diseases like Alzheimer's or even cancer. Detector has also been successfully used to develop an accurate method for the detection of COVID, which could be handy during future outbreaks. Number 5. Fix chronic pain. According to the CDC, about 50 million people in the USA alone suffer from some sort of chronic pain, and it usually tends to get worse with advancing age. Surprisingly, modern medicine offers few reliable cures for it, even if it's a major everyday problem for those suffering from it. CRISPR provides a possible long-term solution as it could be used to modify the genetic structure of the affected area and permanently reduce pain. A few researchers at the University of Utah have come up with a way to switch specific genes on and off, using it to disable the inflammation mechanism that causes chronic pain in cases of disc strain. The technique is still in its early phases, and there are a lot of regulatory hurdles before it's fully realized, though the researchers are confident that it won't be longer than 10 to 15 years before it's widely used to treat debilitating conditions that cause lasting chronic pain. Number 4. Cure HIV and AIDS. The HIV epidemic is easily one of the longest-running disease outbreaks of all time, with an estimated total death count of about 40 million. The pathogen type of retrovirus has so far proven to be resistant to any type of cure. We don't even understand how the HIV virus functions, really, especially the mechanism it uses to infect and spread among human cells. It seems like an incurable disease, though CRISPR provides one potential way that it could be eradicated. One team of researchers from Northwestern University in Illinois has used the technology to identify the genes associated with an HIV infection, which could eventually be disabled to permanently reduce the worst effects of the virus. The team is planning to eventually isolate every cellular and genetic factor responsible for an HIV infection, hoping one day to eradicate the disease that still affects more than 1.5 million people globally. Number 3. Antibiotic resistance. Antibiotic resistance is a major problem for healthcare providers. Due to the proliferation of almost every kind of antibiotic imaginable, pathogens are increasingly growing resistant to known drugs as antibiotics turn them into super varieties of everyday diseases. According to a Lancet report in 2019 alone, antibiotic-resistant diseases may have led to more than 5 million deaths worldwide, making it one of the leading causes of death in general. While there aren't any quick-fix solutions to the multifaceted growing problem of antibiotic-resistant pathogens, CRISPR could offer a few long-term solutions. For instance, a team from Canada recently turned off antibiotic-resistant genes inside specific types of bacteria during one of their studies, only it was done on mice instead of human subjects. Other efforts in the same direction involve something called bacteriophages, a type of virus that infects bacteria, which could be modified using CRISPR to attack the antibiotic-resistant regions of harmful pathogens and render them harmless. Number 2. Resurrect extinct animals. Bringing animals back from the dead may not always be as cool as it sounds, as the Jurassic Park franchise adequately proves, though It may have its uses. If it could be done, the idea can allow us to study and maybe even repopulate the planet with long extinct species, and may even open the door for further research into the higher arts of human resurrection. Many teams are working on it, though none have truly been able to resurrect a dead species yet. A major problem is the availability of the entire genome of the said species, which is required to do any kind of CRISPR editing. One American geneticist, George Church, is confident that his team can resurrect the woolly mammoth by 2027, as they're currently identifying all of the traits that separate mammoth species from the elephants that we have today, which could then be used to replicate it on the DNA level. Number 1. Hack the human DNA. For the first time ever, CRISPR has allowed independent researchers to tinker with the building blocks of life itself, raising many ethical and moral questions along the way. It's obvious that once this technology is really out of the bag, it had inevitably used to do the unthinkable, modify the human genome itself. It's possible that within our lifetime, scientists would be able to control a wide variety of human genetic expressions with CRISPR, including resistance to specific diseases, facial features, athleticity, intelligence, or really any other.
Okay, I think that was my last slide, and I think, we'll quit here, and I'll stick around for a little while. And see you next time. It's Levi. Okay, folks, I think, sorry, we ran about 10 minutes over, but I think the last one was kind of cute. This is obviously not David Letterman. And so there are some, okay, so this was some brave new word. These are some of the traits that could be modified. And this is one of George Church's lecture type of thing as to it can, but again, that's too much futuristic. So I think we'll stop here. I will stop my screen share and stop the recording. Okay, folks, I think let's stop the recording first. So, oh yeah, I think. No.
Well, that
Okay,
was
yeah. Oh yeah.